All right, here we go, guys. Mr. Rice is here. I'm doing example 4 for our exponential growth and decay. And what I'd like to do here is look at that. I would like to go over a different type of problem with you with exponential growth and decay. This is called Newton's law of cooling. So this is a Newton's law of cooling problem. I'm going to zoom into my other work here. Okay, so Newton's law of cooling states the rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. Suppose a metal figurine heated to 150 degrees Fahrenheit is brought into a room having a constant temperature 72 degrees Fahrenheit. I don't know why I'm reading this, guys. You guys can read, right? So, but the basic idea here is that we're looking at how long it will take for the figurine to reach a temperature of 100 degrees Fahrenheit. So anytime we see something that deals with Fahrenheit and cooling or heating something up or cooling something down, we're going to be using Newton's law of cooling. All right, so here's how we're going to write this. So we're going to write this to start with. We're going to write as starting with dy dt, and we're going to say that's equal to k times, all right, what do we need it to be times? Well, y is my temperature. Okay, so it's the difference, it's proportional to the difference between the temperature of the object, okay, so that's y, minus the temperature of its surroundings. So what's the temperature of the surrounding? Well, suppose a metal figurine heated to 150 degrees Fahrenheit is brought into a room having a constant temperature of 72 degrees. So the surrounding temperature is 72. So that's what we mean by the difference. So y minus 72. Well, now that we have that guy, that will be nice because we will now be able to take the antiderivative. So we're going to end up with we're going to bring the y minus 72 over. So we're going to have 1 minus y minus 72, 1 over y minus 72, dy, equals k dt, all right, when we separate the variables. All right, so now we're going to do that, and we're going to get ln of absolute value of y minus 72 equals kt plus c. All right. So now I'm going to solve for y. So I'm going to get y minus 72 equals e to the kt plus c. And we'll call this c. Well, we'll just leave it as c. c1, c1. All right. And then we're going to get y equals, and now remember this e to the c from the previous problems, e to the c comes as c e to the kt plus 72. Right? Okay, so now that we solved for y, we're going to need some conditions, initial conditions to solve for c and for k. So the first thing we're going to do, all right, so first step is we're going to use 0, 150 because that's the initial temperature, right? Initial at 150, and we're going to use to solve that for c. All right? So this is t, time equals 0. This is y, 150. So we're going to go and plug that into my that right there, to my equation. So I'm going to have 150 minus 72. Or I can just do, I mean, it's better to do 150 minus 72. So 150 equals c e to the kt, so t was 0. Plus 72. So I'm going to subtract 72 over. And e to the 0 is just 1. So I'm going to end up with 78 equals c. All right, great. So now we have, let's see, I'm going to go back to green. So now, right now we have y equals 78 e to the kt plus 72. So now we need to find k. So we're going to go and find k by using our second bit of information. Ooh, what did I just do? All right, so we're going to use our second bit of information. 150. Okay, so if the figurine cools from 150 to 120 in 15 minutes. So that's our second piece of information. Okay, our second piece of information now is that T is 15 minutes and Y is 120 degrees. And we're going to use that to solve for K. Okay. So now we have 120 equals 78 e to the K times 15 plus 72. All right, so we're going to subtract 72 over, so we'll have 48 equals 78 e to the 15k. I'm going to zoom in here so you see my work. Divide by 78, so 48 over 78 equals e to the 15k. Solve for k by taking the ln of both sides there. So we're going to have ln of 48 over 78 equals 15k. That gets rid of our e. So k is going to equal 1/15 times ln of 48 over 78. All right. Now, if I put that in the calculator, that's approximately equal to approximately equal to negative 0.0323. All right. Okay. So now I have my equation. All right, let's rewrite this guy. Come on. All right, so now we have y equals 78 e to the negative 0.0323 times t plus 72. Okay, so now we're going to go ahead and solve for t with our last bit. So, you know, you're just like, man, I thought that was the whole thing. Geez, this problem's taking forever because it says how long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit. So now, finally, we're looking for t, comma, 100 degrees. So we're going to solve for t. So we're going to put 100 equals 78 e to the negative 0.023, 0.323t plus 72. We're going to subtract 72, get 28. Divide by 78. And then finally, take the ln, well, not finally, almost finally, take ln. We'll get negative 0.0323t, and then we're going to divide that over, right? Divide it to both sides, and we're going to get t equals ln of 28 over 78 divided by negative 0.32, negative 0.032, 23. Now, what we could do to get a better estimation, this is going to be about 32 minutes. We could do to get a better estimation than 32 is we can, instead of putting k right here like this, I could have just made this, like I could have just written, let me use a different color here to show you what I'm talking about. I could have just did this. I could just said this is k, 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 and then in my calculator, once I did this in my calculator, I was going to put in this whole thing right here. I would put that in right here, and that's just going to give me a little bit more accuracy in my answer. But either way, you're going to get the right answer here if you do the work as follows. Okay, guys, There is my other example for exponential growth decay. This is called Newton's law of cooling. See you later, guys.